All right, our next example is going to build off of what we just did. So we're going to consider the polynomial t to the fourth minus 5t squared plus 6 over q, which is not irreducible. It factors as t squared minus 2, t squared minus 3. In the splitting field, we know to be, well, we have to have access to the square root of 2, and we have to have access to the square root of 3. Right? So let's let G be the Galois group of q adjoin root 2 root 3 over q. All right. So this is the extension is a splitting field, so it's finite and normal. So we know by the fundamental theorem that the order of G, the order of the Galois group, is the degree of the extension q adjoin root 2. Q adjoin root 2 root 3 over q. And we've computed this a lot of different ways. We know that that is 4. Okay. We also know that there exists an element of the Galois group that interchanges the conjugates root 2 and negative root 2. So there exists some sigma 2 in G such that sigma 2 of root 2 is negative root 2. We also know that root 3 and negative root 3 are conjugates. So there exists some sigma 3 in G such that sigma 3 of root 3 is negative root 3. And in fact, more is true. We know that both sigma 2 and sigma 3 can be chosen to be the identity on root 3, root 2, respectively. And let me just show you how that is argued real quick. The way it's argued is as follows. So as a quick aside, t squared minus 2 is irreducible over q adjoin root 3. Since it's irreducible over q adjoin root 3, there exists, and both of the conjugates are obtained just by adding root 2, there exists an isomorphism from adding root 2 to adding negative root 2. And just a quick reminder on how that was constructed. We take q adjoin root 3 polynomials over that. We mod out by t squared minus 2. And then over here on the other side, let me give myself a little more space. We're going to add in our negative root 2. Okay, so this was undo evaluate at root 2, and then evaluate at negative root 2. Now, of course, the field on the right, this is the same as the field that we're considering. And these evaluation maps are the identity on the coefficients. So they're identity on the root 3 stuff. Okay, so this is sigma 2. So similarly, sigma 3 is constructed. Okay, so this gives us 2 automorphisms. The identity adds a third automorphism. So we have identity, sigma 2, sigma 3. But then the composite sigma 2 composed sigma 3 is also an automorphism. That will choose to negate both of root 2 and root 3. So that's a completely different automorphism, which is the composite. And that is our Galois group. That's G. I think I called it G. And it's helpful to make a table out of this. So I will make a table here. We can see what it does to root 2, root 3, and actually a basis for q adjoin root 2, root 3 over q is 1 the rational number 1, which all of the automorphisms fix, so we're not going to add it. Root 2, root 3, and then root 6. So it's helpful. Your book only does root 2, root 3, but I find it helpful to do all of the non-rational basis elements. So we have 1, sigma 2, sigma 3, sigma 2 compose sigma 3. And we're just going to do what it does to each one of these. So the identity fixes root 2, root 3, and therefore it fixes root 2 times root 3, which is root 6. Sigma 2 negates root 2, it leaves root 3 alone, but root 6 has a root 2 in it, so it's also going to negate root 6. Sigma 3 leaves root 2 alone, negates root 3. Root 6 has a root 3 in it, so it's also going to negate root 6. Sigma 2 compose sigma 3, which happens to be the same thing as sigma 3 compose sigma 2, right? Because if we first negate root 3, then negate root 2, that's the same as first negating root 2, then negating root 3. There's no issue with order there. So I'm going to negate root 2 and root 3. That's what the composite map is. And if we negate root 2 and negate root 3, we're going to get 2 negatives on our root 6. So that's going to be a positive root 6. Okay. So this is what it does to each of them. And let me also notice that G is actually isomorphic to the 4 group, which I forget how people write it out. It's Z2 cross Z2. Okay. And the mapping is as follows. The identity element goes to 0, 0. Sigma 2 goes to 1, 0. Sigma 3 goes to 0, 1. And sigma 3 compose sigma 2 goes to 1, 1. And this map is a group isomorphism. You'll have to go in and you'll have to check that, it behaves nicely with respect to the operations, but it does. In fact, the Z2 cross Z2 and G have the same multiplication table. And so that's what the Galois group is here. For this example where we add one root and then we add another root. Similarly, if we were to have, so as a separate example, if we were to add in like a root 2, root 3, root 5, we would get a Z2 for negating the root 2. We would get a Z2 for negating the root 3. And we'd get a Z2 for negating the root 5. And you can extrapolate from these examples how it would be if you added in several roots. And so this is a slight change in the previous video. Instead of just adding in one root, we add several. And what happens is we get a Z2 for every new root that we add.